Alrighty, some physics problems from chapter 11 about angular momentum. I think that's what they're about. It's kind of the mindset that I'm in, so let's see if that's the case. 47, oh yeah. Track is mounted on a large wheel that is free to turn with negligible friction about a vertical axis, and a toy train of mass m is placed on the track with the system initially at rest. Train's electrical power is turned on, and so I'm going to make a little an overhead view of this. Here's the train. Let's say the train's going this way. Kind of looks like that's what's happening. I know a caboose when I see one. The train's going this way at a velocity of 0.15 meters per second. And the train's mass is m, and the track is 1.1 m. And importantly, I kind of wish this wasn't the first problem. I mean, I'm the one who picked these, so I guess I should say sorry about this. But this does have this relative motion aspect to this problem that I didn't really want that to trip you up. But they do say here that this is the speed with respect to the track. So like if you're an observer here looking at this whole thing, the train does not appear to be going this fast to you, because as the train goes this way, because of the conservation of angular momentum, the track is going to rotate the other way, and the track is going, the train is going this fast relative to the track. Okay, so what do we do with that? Well, the velocity of the outside of the track, it's going to be moving this way, and let's just call that the velocity of the, let's see, the track's a little bit bigger, so I'll make that a capital T, velocity of track. Okay, so what is the actual speed of this relative to like the static environment? It is 0.15 minus this, right? So this will be going this fast. If the track was going exactly the same speed this way, and the train was going 0.15 meters per second the other direction relative to the track, then it would be like watching somebody, those moving sidewalks that you see in airports sometimes. If somebody's walking the wrong way on it and they're walking the same speed as the track, it would look to you, not standing on the moving sidewalk, that they're standing still or walking in place at least. So it's just this minus that. That is the actual speed of the train. And what we need to do here is recognize, in terms of angular momentum, that the angular momentum that the system had initially is 0, and that means that the angular momentum that it has after the train's turned on also has to be 0, which means that the angular momentum of this must be equal, opposite in direction, to the angular momentum of the track going the other way. So if we're not paying attention to signs, you could just say that the angular momentum of the train would have to be equal to the angular momentum of the track. And we could put those in absolute value signs if we wanted to. I wouldn't fuss at you if you didn't do that. But since everything is 0 to start with, they have to be equal, but opposite in direction afterwards. So what's the angular momentum of the train? There's two ways you can imagine that the train is kind of like a little piece of a hoop with rotational inertia mr squared. So you could do like an I omega thing. Or you could say, well, the train's kind of smallish relative to the track, so you could do like an r m v sine theta, which would be the sine theta is just going to be 1. You could do either one of these. I'm going to show you here that those are in fact the same, because this would be mr squared, and then this omega would be v over r, and one of those would cancel. So whichever way you do it, it boils down to this, the rmv, and that's the v of the train. That would be equal to the I omega of the track. And I think this is what we're looking for, right? What's the angular velocity of the track? All right. So let's just fill in some of the details here. So the radius of this is 0.43. The mass of the train is just m. The velocity of the train relative to the world is 0.15 minus vt. And that's equal to, the track is like a hoop, that's m r squared times omega. And we got two unknowns in here. This is the velocity of the track, and this is the angular velocity of the track. Since we're trying to find this one, I can substitute here. V is equal to omega times r, right? And while I'm at it, one of these m's, well, I guess that's all of those m's cancels out, and one of these 0.43s can cancel out. So here I have 0.15 minus velocity is the same as omega times r. And so over here I have 1.1 times 0.43 times omega. Geez, it's a little messy. Hope that's legible enough for you. So what do we end up with? I think I end up with, after doing a little bit of math, that omega is equal to 0.43 times 1. So it looks like I have 1.1 plus 1 times 0.43. You can check my algebra there. I'm just kind of rearranging, doing a little factoring and so on. And it's 0.15 over 2.1 times 0.43. And that's about 0.17 radians per second. All right, that's that one. Sorry, I think maybe I should have picked an easier one to start. Book thinks that's an easier one. I only give it 1 dot. So it still wasn't that hard, but the whole like relative velocity thing I think makes it a level of difficulty that we're not super interested in. Okay, 51. A wheel is rotating freely at an angular speed of 800 revolutions per minute. We'll convert that if we need to in a sec. On a shaft whose rotational inertia is negligible. A second wheel, initially at rest, with twice the rotational inertia of the first, is suddenly coupled to the same shaft. What's the angular speed of the resultant combination of shaft and 2 wheels? And then what fraction of the original rotational kinetic energy is lost? Okay, so L initial is equal to L final. The initial is the I of the small one, omega, and the final is the I of both of them together times the final angular velocity. So if the new disk, is it twice? So remember that rotational inertias add up just like masses add up. If you couple a wheel, or like if you take a mass and then you put another mass that's twice as much, then you have 3 times the original amount of mass, right? So this is I times 800. I'm just going to keep these units. And then that's 3I, right? Because you have the original wheel, I, and then the 2I one that got added onto it. So those cancel, and we get a final angular velocity of 800 divided by 3. What's that, 267? All right. and the units will be revolutions per minute because I didn't change that. And then what fraction of the kinetic energy is lost? Well, the kinetic energy initial is 1/2 I omega squared. So I don't know what the I is, so this is going to be in terms of I, but we should still be able to do like a what fraction of. So that's 800, and that squared is 160,000. Half of that is 80,000 I. And the final kinetic energy is 1/2 3I times 800 over 3 squared. So that's, I'm writing it as the 800 over 3 because I think I can see more easily what's going on here. So I have one of this 3 and one of those will cancel out, and then I get the same 160,000, half of that is 80,000, and then that's going to be, there's another 3 there, so it's 80,000 I over 3. And what do they want to know? What fraction of the original kinetic energy is lost? Well, we went from 80,000 to 1/3 of an 80,000, so 2/3 of it is lost, right? Let's check the answers here in the back. Yep. That's what they done did said. Number 55. Looks like I have some room here on this sheet. 55 is on the next page. A horizontal vinyl record. Do you know what that is? I bet you do. Those are kind of like retro cool now, right? I was a record collector when I was in high school. I used to drive around with my best friend Ray in my 1972 electric blue Dodge Dart. I used to go to record stores and buy used records, look for cool stuff. A horizontal vinyl record of mass 0.1 kilograms and radius 0.1 meters rotates freely about a vertical axis through its center. Of course it does, with angular speed 4.7 radians per second. I wonder, you know what speed records spin at? There's 3 speeds. There's 33 1/3 RPM records. That's like the classic, like long play LP, like 5 songs or something like that. One side of a record. And then there's 45s. Those were singles. 45 RPM. Those are like the little, like 7-inch things. And then the real old ones were 78 RPM. Those were like the ones that played on like a Victrola, where you had like the hand crank. Like my grandfather had one of those machines. So I bet you if we converted this, which I'm going to do right now just for fun, to RPMs, that it would match up with one of these, because the people who write the book Problems are, they're no fools. So if you want to convert 4.7 radians per second to rotations per minute, 2 pi radians is 1 rotation, and 60 seconds is 1 minute. So that would give you rotations per minute, or RPMs. So I need to take 4.7. This is not part of this problem, sorry, I'm just doing this for my own entertainment. Divided by 2 pi, don't forget those parentheses, or you could do the little, make it look like a fraction thing with your fancy calculator, and then times 60. So this is a 45 RPM record. That's like a single 7-inch record. Oh, I guess we could have done the conversion on this too. I wonder if the, let's see, hold on. So they're saying it's 10 centimeters, so that should be about 7. 10 centimeters is about, well, that's no good. Let's go from the other end. 10 centimeters is about 4 inches. Oh, that's the radius. So the 7-inch would be, they were about 7 inches across. That was the diameter. All right, sorry, there's that nostalgic music time is now over. Let's get back to physics. The rotational inertia of a record is about 5 times 10 to the negative 4th kilogram meters squared. A wad of wet putty of mass 0.02 kilograms, 20 grams of wet putty, drops vertically onto the record from above and sticks to the edge of the record. What's the angular speed of the record immediately after the putty sticks to it? So this is kind of like the kid jumping onto the merry-go-round. It's not kind of like it, it's exactly like that. Except for, in this case, the record, the disk is moving and the particle is attaching afterwards. So we have initial angular momentum equals final angular momentum. Initially, I have the I omega of the record, and then afterwards, I have the I plus the mr squared of the particle that's sticking to it, right? Rotational inertias just add up like masses, so you just add the particle there, plus mr squared, times the final angular velocity. And that's it. So that should be real easy for us to do, I think. So I got 5 times 10 to the negative 4th times 4.7 is equal to 5 times 10 to the negative 4th plus r squared, right, because it's stuck to the edge of the record, so that's like at the full radius there. I plus mr squared times the final angular velocity. Time for calculator. Let's make it look like a fraction. Should use that feature. I'm still not used to having one of these fancy calculators. So that's 5 times 10 to the negative 4th times 4.7 over 5 times 10 to the negative 4th plus 0.02 times 0.1 squared. .36, or they're going to call that 3.4 probably. Radians per second. Let's check that. Was that 55? Yep. I sure enjoyed that little nostalgic trip on memory lane. 57 and 59 we're doing also. A uniform disk of mass 10 m and radius 3r can rotate freely about its fixed center like a merry-go-round. A smaller uniform disk of mass m and radius r lies on top of the larger disk, concentric with it. So like a little Tower of Hanoi kind of thing. You know what that is? It's a little disk stacking puzzle where you're not allowed to put a bigger disk on top of a smaller disk, and there's like three posts, and you have to move all the disks. They start out like that, and you have to move them all onto this one. But you can't ever put a bigger one on top of a smaller one. So you have to play this little game where you bounce back and forth and so on. And, interestingly, it takes 2 to the n minus 1 moves to get, this is like n equals 4, right? If there's only one disk, then it only takes one move. But if there's two disks, it takes 3 moves. because you would go, if you just had two, you move this one here, the little one, and then you move the second one over to here, and then the third move is you put it on top, and you've moved it. And then it turns out, oh, never mind. It's a cool math problem, but that's how many moves it takes. There's some Buddhist monks somewhere, or some Buddhist, not philosophy, that's the wrong word, lore, I guess, something like that, that involves like a giant Tower of Hanoi puzzle with like 100 discs on it, and these sort of fictional monks who are moving the discs back and forth, like eventually trying to solve the 100 disc puzzle. And when they finish, that's when the world / universe ends. So enjoy yourself now. Okay, so the initially the two disks rotate together with angular velocity of 20 radians per second. Then a slight disturbance causes the smaller disk to slide outward across the larger disk until the outer edge, catches on the outer edge of the larger one. Afterwards, what then is their angular velocity? Okay, so they're starting like this, with the I is just, the smaller one is just M and R, right? So that's two disks, so I have 1/2 M R squared plus MR, 1/2 MR squared. That's the little disk. And then after that, here's a top view. The one, this is 3R, so now the smaller one has slid out to here. So this would be like, these three segments here would all be like R, R, R. That's the radius of 3R of this one, and then this one has slid over to here. So that has been parallel axis shifted by, it was here and now it's here, so that's an axis shift of 2R. So the new rotational inertia of the little disk is its old rotational inertia, 1/2 mr squared, plus parallel axis shift, m times the shift is 2r. The center of mass was here, now it's here. So that's 2r squared. That's how the parallel axis theorem works, right? M times shift squared. And that is 4 mr squared plus 1/2 an mr squared, so that's 4.5 mr squareds. That's the new one. So we're going from having a rotational inertia of this, which is 9 times 5 plus 1/2. And what's the omega is 20. To having this, the 45 has not changed. It's still 9 times 5, so 45 plus 4.5. So, make sure I got all the details right. Yeah. Okay, so the mr squareds cancel, and I get that the new angular velocity is 18.4. radians per second. And they want to know what's the ratio kinetic energy to K sub 0 of the new kinetic energy of the two-disk system to the system's initial. they want to know, sometimes College Board asks questions like this, what's the ratio of? And you just set up the ratio and then simplify it. So it's that. So let's see, the initial kinetic energy is 1/2 I omega squared. And the final kinetic energy is 1/2 I omega squared. So let's see, the 1/2s cancel, the MR squareds cancel, so it's really a matter of 49.5 times 18.4 squared. Divided by 45.5 times 20 squared. Ooh, I almost made the parentheses error there. 45.5 times 20 squared is 400. Everybody knows that. So 0.92. So we have 92% of the original kinetic energy is still there. That's one way of looking at that number. Check our answers. 40, 57. Yep. They rounded that to 18 because sig figs. All right. And one more. Number 59. Figure 1152, there's a little figure there. There is a stick that has an axis in the middle, and then there's a little red dot here at the end with an arrow that looks like that. I don't know what that means yet, but I think maybe this stick is going to come along and whack it or something. Is an overhead view of a thin uniform rod of length 0.80 meters and a mass m. And it's rotating at 20 radians per second. And that's before anything happens. Call that omega initial. A particle of mass m/3, initially attached to one end, is ejected from the rod and travels along a path that is perpendicular to the end at the instant of ejection. If the particle's speed, Vp, is 6 meters per second greater than the speed of the rod end just after ejection, what's the value of Vp? Okay, so this is one of those things again with the relative motion thing. Kind of like, what was it, 47, the first one that we did with the train? Okay, so this thing has a velocity Vp, and they're telling us the relationship that Vp is 6 meters per second faster than the velocity of the end of the rod. This is a P, and that's an R. And that's the end of the rod, just to be clear. Okay, so we're going to need that relationship at some point. All right, so let's see if we can figure this out. We want to know what is the value of Vp. So initially, what do we have? Actually, I should say this is the L final plus this, why am I including this lowercase l? Not to be confused with the length of the rod. That's the momentum of this thing, which we're now going to think of as a particle relative to this point, right? So this is I omega, that's I total, times omega initial, is equal to the I of just the rod, because the particle has been ejected at this point, times omega final, plus RMV sine theta. The sine theta doesn't matter if we go right here, because the sine theta is going to be 90 degrees right at that ejection point. So R, the radius here, that R is half of that. Actually, I'm not going to plug numbers in yet. I'll do that in a sec. R M V of the particle. All right. So, time to start carefully plugging some things in. What is the I total? Well, the I total, this is a rod about its center. The rotational inertia of a rod about its center, that's one that we're supposed to know. 1/12. Mass of the rod is m. The length of the rod is 0.8. Square that. 1/12 m. Oh, we need the I total. And there's also a particle stuck to it, which has, you want to add a particle, you just do the mr squared of that particle. So its m is m over 3, and its r is 0.4 squared. So sorry about that accidental close parentheses. You think it'll look better if I just scribble on it some more? Maybe? Maybe not. Times omega, initial. Oh, more scribbling. So this is, sorry, I can squeeze a 20 in there. There we go. Okay. And then afterwards, they separate, and we have the rotational inertia of the rod by itself, which is 1/12 m L squared, plus RMVP. So R is 0.4. The mass, this is the mass of the particle, that's m over 3 times VP. Okay, I think we look pretty good here. Actually, wait, I feel suspicious. Oh, geez. I didn't even, over here, the I, oh, wait a minute, hold on. Oh, I know what I did wrong. I was wondering why I wasn't going to need to use that, and that's clearly wrong. So it's this, I just left that out completely. Omega final, that's the problem. Okay, so I have two variables. I need to somehow recast omega final in terms of VP, right? So here I just need to recognize that omega final, that's the omega of the rod, is equal to, omega is equal to V over R. So that would be the V of the end of the rod over R, which is 0.4. And of course, V sub R is VP minus 6. So I need to substitute that for there, and then do a whole bunch of math. Strap yourselves in, kids. Let's see, I think I'll go ahead. Did you notice that there's an m in all of these terms, so that cancels out? So here I've got 0.8 squared divided by 12 plus 0.4 squared divided by 3 times 20. I think I'm good on that side, I hope. And then here, I think I'm going to have to do a couple more steps here. So I'm going to do 0.8 squared divided by 2. That's like 0.32, right? Oh yeah. 0.32, oh, times, dang it, more scribbling. VP minus 6, 0.4. plus m's cancel, 0.4 divided by 3, is that 0.13, I guess? 0.13 VP, right? I just got to make sure. Okay, so I'm good. I have an equation, just some baby algebra necessary here, but I think I need to do it. I'm not going to try to crash through too many steps. This is very, like this kind of detail, this sort of mundane mathematics, this is not typical of College Board problems. It is, you know, can happen in our book problems, but we're not afraid of some math. So 0.8 times VP, and then minus 6 times that's minus 4.8, right, after I distribute the 0.8 to that, plus 0.13 VP. Okay, so we're nearly there. So that's going to be 0.93 VP equal to, adding this over here gives me 6.93. Boy, I sure hope I get this right. I'm going to feel pretty good about myself. And that gives me a VP of 7 point, what are they going to call that? 7.5, I bet, meters per second. And just before I even check that, just let's see, does that make sense? This little particle was ejected from the end of the rod, and it's going 6 meters per second faster than the end of the rod. So that makes sense, that it got ejected and it kind of slowed the rod down quite a bit, a factor of, well, I guess I'd have to figure out but it slowed it down so that the end of the rod is only going 1.5 meters per second now. So let's see if that's right. Nope, it's not. Dang it. The answer in the back of the book seems to be not that. They have 11 meters per second. Oh dear. Well, where did it go wrong? This is 100% the right idea. I can promise you that. What I did wrong, boy, oh boy. Oh. Well, that would make a difference here. I feel like I'm so lucky that I just spotted that. I have a 1/2 here. That should be 1/12, not 1/2. All right, maybe a quick fix. Let's give it a shot. So instead of 0.32, this would be 0.8 squared divided by 12. Oh, that's a little different. And I think the theme of this problem seems to be scribbling. 0.053. Okay, so that is going to change these. So that divided by 4, nope, just kidding, divided by 0.4 is 0.13. And 0.053 times 6 is 0.318. You know, I had this weird feeling when we got that 4.8, and I was like, that seems awfully big compared to the other things here. But I just went along with it. So 0.13 and 0.13, that's going to be 0.26, and then adding this much smaller number over here is going to be 2.45. 2.45 divided by 0.26. No, this is still not right. Ah! Dang it. Well, Well, I don't know what to tell you. I think that I'm going to have to leave this one here. And if I could figure out what the problem was with that, I will make a comment for you. But I don't think that there's any kind of structural issues here with the way that I set up the problem. I think everything is good. And we got closer anyway. All right, there you go. Sorry about the confusion. And cheerio.